let's get started. Now, today the topic is going to be on Gauss's law. Last class period, we talked about Coulomb's law, and we saw how to solve problems with Coulomb's law. Today, we'll see how to solve problems with Gauss's law and how to differentiate which law to use to solve a problem. So, getting started, we very briefly mentioned Gauss's law in the general physics class. Gauss's law is something that they can do, but it uses calculus ideas, so it's something I spend a lot more time with you on than with them, even though you're not going to use much calculus with it. So here's his actual name, Carl Friedrich Gauss, and he came up with the idea that I can tell you how much charge is enclosed if I know how much electric field lines are coming out of a region. And so that gave him, or brought forth, the word flux to be applied here. Flux, which, as I understand, is a derivative of fluctuation, or no, not fluctuation, fluxion, means how much is going in or out of a surface. And here we're going to talk about electric flux. When we get to magnetism, we'll also have to talk about magnetic flux. So it's how much field is going out of the surface. So basically, the purple here is Gauss's statement. I can tell you how much charge is enclosed if I can determine what the field lines are entering or exiting a box of any shape. Has to be a closed box, though. You can't have, there's this much that comes out of these areas, and then I don't know that other area. It has to be completely enclosed. So first, calculation of flux. These are actually slides that I have for the general physics when I use more time and cover it there. On what flux means. It's easiest for me to think about talking about the weather. Right now, we are in the winter time. What does it mean that we're in the winter time? Okay, temperatures are lower. But why are temperatures low? That's a perfect answer, Nate. I don't want you to feel like I'm saying, no, that wasn't the right answer. Why are the temperatures lower? No, we're closest to the sun.
Because we get less sunlight because of where we are on the surface of the earth.
Yes, that's a very common misunderstanding. A lot of people think that it has to do with how close or far you are. But if that was the case, it would be winter in both hemispheres at the same time. But it's not. They're in the middle of summer in the southern hemisphere. It has to do with the tilt of the earth. That is, the earth orbits the sun in a plane that we call the ecliptic, and the earth is tilted. So here's the earth. It's tilted so that there is a 23.5 degree angle difference between the axis of the Earth's orbit about its axis, right, we're spinning, and the axis of the Earth's orbit about the sun. And because of that, the sun is at the center here. Here's the sun, and it's sending off radiation, and right now, in the picture shown, what part of the Earth is getting the most radiation? The lower part, right? If you cut the Earth in halves to get hemispheres, that cut in half goes like this, and the sunlight does hit the upper part up until you get to 23.5 degrees. If you're close to the North Pole than 23.5 degrees, on the date when the Earth is, the most at the extreme, what we call the solstice, the sun never rises or sets. And if you go closer than 23.5 degrees, it's more than a day. The sun never rises or sets. So if you're at the North Pole, you'll have a couple months where the sun never rises or sets, because you're always in the shadow of the Earth, even when you're on the side that's, quote, toward the sun. So that's the big reason. Because of the tilt, we receive less time in sunlight right now in the northern hemisphere. Southern hemisphere, they receive more time in sunlight. Because I'll use another vertical or line. This vertical line here, the only stuff that's in sunlight is on the left of that. Anything on the right of it is in shade. But there's a second piece to it. Where on Earth is it getting the most direct sunlight? In this picture.
Like the tropic south of the equator.
Yes. The tropic of, I think it's Capricorn is south and Cancer is north. That's how we define the tropics. The tropics are 23.5 degrees north and south of the equator, and they're the regions. If you're in the tropics, at some point during the year, the sun's going to pass directly over your head. We're north of the tropics here, so the sun will always be south of us. So the most direct sunlight in this picture is right here. Because it's the most direct, if you put a solar panel flat on the ground, you would gather more energy at that location than anywhere else. If you went to somewhere like up there at the equator in this picture, the sunlight would be coming at a 23.5 degree angle, and you would be collecting less because the area seen by the sunlight is smaller because of the angle it's coming. Do you understand what I mean by the area smaller that sees? So, since it's not perfectly clear, I'm actually going to draw another picture. Well, actually, this picture is perfect for that. If this same object here was oriented like this, it would look like more area to the sunlight because of the angle. I think it actually goes farther than that because the angle, it coming in directly. So the cross-sectional area is what we talk about. The cross-sectional area is if you were to stand back here and look at it, cross-sectional area would be how much area does it take in your view. The bigger it is, the bigger the cross-sectional area. And so the angle makes a difference. And so the flux is going to be a measure of how much sunlight actually hits in my sun analogy, or how much electric field goes through a surface with the true analogy. And so actually, if you look at the picture on the right, you can see that the A cosine theta is the cross-sectional area, the effective area of that larger area that's at an angle to the light. Or in this case, we're talking about electric fields. You have a question, Gabriel?
The K's that are italicized in the equation, are those different than, like, on the right-hand side area?
The A's are also italicized in the figures. It's just the italics are not nearly as slanted. Okay. So they're the same. So when we talk about the flux, we're talking how much electric field goes through. To get the final thing on this to make sure it's understood, how much electric field would go through if I had my object oriented like that? None, right? So we define the direction for the area as the direction normal to the surface. So here in this picture, it shows that dashed line is the direction normal to the surface. Same idea we've talked about before. And theta then is the angle between the normal to the surface and the electric field. And given that, then the effective area is the area times cosine of that angle between the normal and the electric field. And so the flux is EA cosine theta. No calculus involved in that, right? Of course, there is calculus involved in really calculating the flux because this was for a nice flat surface, and if you have a curved one, you're going to have to do more. Brady has a question.
Just a notation question. Don't two lines mean parallel?
Yes.
It's supposed to be perpendicular?
No.
Okay.
Because we define the direction of the area as the normal to the surface. That's why it's parallel.
Okay.
Right? It's when you have a surface like this and you want to define direction, the only two directions that are unique are up or down, right? Into it or out of it. And so that's why you define the area to one of those, and out of it is the convention. And so parallel means going straight through it. Okay, so there is the basic, how we calculate flux. Here's the full equation, and I know I've got the aspect ratio off on this one. That's what happens when you change from one slide size to another. But the flux, the symbol is the Greek letter phi because that's the F sound. Subscript E because it's electric flux. is the integral of E dot dA. So that's the flux for a given surface. And so you're going to integrate over the area. So that's a two-dimensional integral if you're integrating over the area. And already people are probably starting to feel a little uncomfortable. But once again, don't worry, we're actually not going to do calculus virtually any time we use this. If we use calculus, it's much more going to be to calculate the charge enclosed than to calculate the flux. So when we use Gauss's law is the total flux on a closed surface. So for Gauss's law, the flux for Gauss's law, because it's on a closed surface, is this. What does the circle on the integral sign mean? It means it's a closed surface. And sometimes you'll see people write this with a double integral because since it's dA, it has to be two integrals. It means the same thing, really. It's just more explicit when you put the double integral sign. So this will make a lot more sense when we get to using it. So I'm trying to get the basics out, and then we'll use it. Gauss's law, the flux is equal to charge enclosed over epsilon 0. So what we're going to do for Gauss's law is we're going to use this equation, and we're going to calculate the flux separately from the charge enclosed. Some people think, oh, if I calculate the flux, then I know what the other side of the equal side is as well. That is very true, but usually we're trying to either find the charge enclosed or find the electric field. So we want to do the two sides separately and then solve for what we don't know. And don't simply say, if somebody says find the flux from the charge enclosed, they forget that you can work on both sides. So what I've said not very clearly, when you're using Gauss's law, make sure you work the left side separately from the right side and then set them equal. So, in our homework problems, the homework assignment that was supposed to be due today that clearly I postponed a week because we haven't talked about it yet, some of the problems will require you to use Gauss's law. Some of them will require you to use Coulomb's law. The truth is, you could solve all of them with just one of those two laws. But the practical is, sometimes it's easier to use Gauss's law, sometimes it's easier to use Coulomb's law, and the two are absolutely equivalent to each other. So you want to make your choices based on what's the easiest. Now, as I've been emphasizing, calculating the flux can be really difficult. And so now I might give you a homework problem, that comes from mastering physics, expert TA. It's been like 5 years since I used mastering physics and I slipped up. I might give you one that says calculate the flux on a surface and gives you some geometry where you actually have to do the calculation, doing the integral. But that's not going to be a likely or common occurrence. What's going to be common is exploiting symmetry. If you can exploit symmetry, then Gauss's law becomes super easy. That's what you like, right? If you can't exploit a symmetry, then usually Coulomb's law is going to be easier. So I told you the first problem on the homework, your concept is going to be Coulomb's law. Why Coulomb's law? It doesn't have an exploitable symmetry. So we need to go through what's an exploitable symmetry so you understand how to make those decisions. So start with what would make something exploitable? I don't think I have it laid out. Nope. What would make something exploitable? Okay, if I can define a shape, these shapes that we use for Gauss's law are not real objects. They're shapes we use exclusively for calculation. And so you can think up any shape. But what you want that shape to do is have either electric field equals 0 on a surface, or electric field is perpendicular to area on the surface, or electric field is constant and angle between electric field and area is constant on surface again. If you have one of those three conditions, then Gauss's law, if on every single surface, if you have one of those three, then Gauss's law can be done trivially. And so that's what we're looking for. So we need to identify shapes that would give us that kind of symmetry. So let's start with, now I'm not asking you to use your clickers. I don't even have the clickers thing set up.
You blocked the last screen.
Oh, you need to scroll down. On surface?
Yep.
We all good?
Yep.
Okay. So I'm not asking you to use clickers. I don't even have it turned on, so there's no point in getting out a clicker. But just answer for me, what type of exploitable symmetry does a sphere have? Does it have a spherical symmetry? Does it have a cylindrical symmetry? Does it have a planar symmetry, or does it have no symmetry? I chose the easiest one. Okay, a sphere has a spherical, or a sphere has a spherical symmetry. That's a given. So if a sphere has a spherical symmetry, then I can make a spherical Gaussian surface, an imaginary surface, to make Gauss's law easy for me. So let's just take an example before I go to that question of a sphere. Yeah, let's make the sphere have radius r and charge plus q. And I ask you to find the flux, to find the electric field at some distance r away. The first thing I need to do is say, does it have an exploitable symmetry? And you said, yeah, it has a spherical symmetry, so probably is exploitable. And because it's spherical, what shape should I use for my Gaussian surface? A sphere. Now, of course, on paper, it looks like a circle. A kind of circle. To the best of my artistic abilities, a circle. And so that's my Gaussian surface. It's not something there. It's something for calculation. Now, based on our picture, what direction does the electric field point? Always away, normal to the surface. So the electric field is pointing like this or like this. What direction is the area of the surface of my Gaussian sphere? My Gaussian surface, that sphere, what direction is the area for that? Okay, I didn't hear loud enough.
Normal to the field.
Normal to the surface. Normal to the surface. So normal to the surface is like that. So there's my D. Oh, that's not an A at all. My D area is like that. And of course, my electric field is like that. At all points, what's the relationship between the directions? Electric field is parallel to dA. So that's a start. That was one of two pieces for the final condition. The electric field and the area have a constant angle between them. In this case, 0 degrees. So the next thing is the electric field constant on that surface? Based on symmetry, without any knowledge at all, if you have a spherically symmetric situation, then it can't matter where you are in terms of your angle around it. It can only matter how far away you are. Right? Just because of the symmetry, it doesn't matter what concept you're looking at. With that symmetry, your variation can only occur with radius. So since my Gaussian surface is concentric with my charged sphere, then I'm going to have the electric field at a constant radius is constant. Having those two means, hooray, Gauss's law will be easy. So now let's calculate the flux. The flux is integral of E dot dA. But because E and dA are the same direction, what does the dot product become? Just becomes integral of E times dA. It'd be E dA cosine of theta, but since theta is 0, cosine of 0 is 1, it's just E dA. But if E is a constant, what does that become? And by definition, what's the integral over the entire surface of dA? Yeah. Now, how much calculus did we do here? Really none. But we had to understand what is meant by the calculus and what is meant by Gauss's law. So I have my equation for the flux. Now, what's the area for a sphere? 4 pi r squared. So the flux is equal to E times 4 pi r squared. Now the charge enclosed. The charge enclosed was just plus Q, because I told you that. So that has to be equal to Q over epsilon 0. And so the final step, what's the electric field? E is equal to Q over 4 pi epsilon 0 r squared. Or if you prefer, KQ over r squared. Now, why did I do such a simple problem? To make sure we understand how to do that simple problem, because you're going to do it, I don't know, probably 8 times or so in the homework, right? The one that's due a week from today. So it's good to do that. Aaron? Go ahead.
If you scroll down a little bit, I think it's sigma sub 0.
Yes. You think correctly.
So when you said that equal to Q over sigma sub 0.
It's epsilon 0. My bad. Not sigma. Sigma would look like that.
Oh, okay. The epsilon sub 0 is then what's actually, could you do the step in between there? Just
There actually is no step in between because it's charge enclosed over epsilon 0. That's the equation.
mm-hmm.
And so I'll just go back to the equation. So we spent all of our time doing this, right? And then I had given you that charge Q was the charge on the sphere and the sphere is completely enclosed. So if you want an intermediate step, it would only be that. That's the only possible intermediate step I could have given besides what I wrote. Because the rest is just using Gauss's law. So here, I'll write it. Now we have every possible step.
Mm-hmm. I'm starting to see it. If we keep going.
I was telling a student yesterday, I didn't learn this in my general physics class because I took a non-calculus based one. And then I did direct to steady electricity and magnetism, didn't learn it there either. So when I got to graduate school, I was like, what? And my teacher, when he gave, if he'd give an assignment like this to start the class, I would have been like, oh, I am screwed. Because, I was. That was something I missed out on. Okay, a question for you. This is one you can answer now real quick and easy. What's the flux through a sphere of radius 5 centimeters that has a point charge of -2 microcoulombs at its center? There are two ways. What's the simple way of doing this? Do what?
The way we just did.
Well, this is finding the flux. And I found the flux by doing, well, hand waving for the integral. And then I set it equal to the charge enclosed over epsilon 0. In this case here, since it just asks what is the flux, what's the easy way? Yeah, charge enclosed over epsilon 0. All I can do is, I'm not going to even write down, just do minus 2 microcoulombs over the value for epsilon 0, and I'm done. Because that has to equal the flux enclosed. I could have also, remember I said when you're actually solving problems, you need to do the two separately for getting to your answer. I could have also done it by doing just calculating the flux and using Coulomb's law. Coulomb's law says that the electric field out there is KQ over R squared. And so if I use KQ over R squared for the electric field, and then given my symmetry, I just multiply that by the area, right, going through the steps of our integration we didn't have to do. Then I'd have 4 pi R squared, or times KQ over R squared, and I would end up with the same result. So there's two ways of doing it, but it's obviously a little more difficult, not hard, but a little more difficult doing it with the Coulomb's law in that case. That's why we like to use Gauss's law as much as possible. But we can also use to find the electric field like I just did. I kind of did things out of sequence, so this is not some shocker. We already did it. So when we're using Gauss's law in real life, like on your homework problems, we could have a one-dimensional distribution of charge, that is a line of charge, a two-dimensional distribution of charge on the surface, three-dimensional spread out in 3 dimensions of space. And so we have to look and consider our charge densities, if it's a one-dimensional, two-dimensional, three-dimensional charge density. And that's actually where we're going to do calculus in this. In one of your homework problems, you have a charge density that's, I think, equal to an exponential, right? And so when you're doing the charge enclosed, you have to do the integral. If you're trying to find the electric field closer than the outer portion, the charge enclosed is going to be an integral that goes out to the radius you're looking for. If you're outside of it, it'll go out to the full radius of the object. So that's where calculus is coming into play. Another non-clicker-ish question for you. What type of exploitable symmetry does an infinitely long straight wire have?
None.
Has what?
None.
None is not the answer. It seems like one. Cylindrical. Cylindrical because if you put a cylinder around it, of course, infinite length cylinder, then you would have no difference depending on where you are. Now, for calculational purpose, we use a cylindrical piece. That is, we're going to put a cap on our cylinder. So we're kind of breaking the cylinder, but we know we have cylindrical symmetry for the electric fields. The electric fields are always going to have to go, if it's a positive line charge, they're going to have to go out. And if it's infinitely long, then there's going to be as much charge above as below. I know it starts to sound wicked because you're like, well, what if I move up? It's still infinitely long, so there's still as much above and below, even though there's now more below than there was before. So that means your electric fields are always going to have to be going straight out away from it. So here's a picture, whoops. Here's to find the problem. Charge is spread uniformly along a long wire, long thin wire. Long thin wire is physics code for treat it like it's infinite in length. Infinite wires don't exist, right? But a wire that is long and thin means a wire that is much farther, both ends of the wire are much farther from you than your distance from the wire. If the two ends are much farther away from you than your distance from the wire, like 100 times farther, then it seems like it's infinite. It's a good approximation to treat it as infinite. So the long is just code for treat it as if it's infinitely long. And then I actually got I said very long wire. We want a distance r away. and we're far away from either end. So here's a picture showing the electric fields. Based on symmetry, you know the electric fields have to be going out if it's positive charge, coming in if it's negative. And the problem gave that the charge was distributed with a constant charge density, lambda. So we're given constant lambda. So I'm going to make myself a little imaginary cylinder that's already drawn for me. It's a perfect cylinder, unlike anything I would have drawn. And so this cylinder has some height. Oh, don't use the same color. Has some height h and radius r as shown. So if I have a constant charge density lambda, that is, lambda is the charge per unit length, how much charge is enclosed by my little box? Right, since we have lambda charge per unit length, and h is the total length enclosed, it's just going to be lambda h. So I've done the right-hand side pretty much already, right? Because I take that divided by epsilon 0, and that's my flux. Now we have to calculate the flux on each surface. How many surfaces do I have on this cylinder? 3. I started showing 2 fingers. 3. So I'm going to calculate the flux on the top, the flux on the side, and the flux on the bottom. So let's start with the top. What can you tell me about the flux on the top?
The electric field lines are perpendicular to the area,
And hence?
and hence that it's exploitable symmetry condition.
It's 0 because electric field is perpendicular to the area, therefore E dot, and I'm doing it since it's a constant area, I'm just doing it that way. The parallel parts are 0 because they're perpendicular. So that made it easy. That's why that was one of our conditions for exploitable, because the flux is 0 if the electric field is perpendicular to the normal to the surface. Or to put it another way, if the electric field is running parallel with the actual plane the surface is in. Question, Freddie?
Okay, so we're looking down at it. So we got a circle.
We have 2 pictures, a side view and a top
Yeah,
view.
so we're doing the top view right now.
Okay.
So we had a sphere before.
Uh-huh.
So how is this one perpendicular versus the other one parallel?
Okay, if we look at the top, I'm looking at the left view, the side view. If we look at the top, then we have the area for the top is pointing up. So there's area of the top's direction. And the electric fields on the top are all perpendicular to that.
Okay.
In this picture here, of course, what we would do is we'd put a circle with a dot in it to show that it's coming out.
So by top, you're not saying we're looking at the top, we're saying the area coming out of the top.
Well, we're looking at the area on the top. I'm not sure
I think it's the
where we're
whole
parsing words
vector
differently.
area thing that throws me off.
That the area is normal to the surface.
Yeah, I think that's what's throwing me off.
Okay, so if that's throwing you off, think about it this way. How much of these electric field lines make it out of the surface? They're all staying in the surface, right? So none of them get out, hence there's no flux. Okay, what about the side now? What's the angle between the electric field and the normal to the side? Okay, it's constant and 0. We saw that on the last one. If it's constant 0, then we have to look at what's the magnitude of the electric field going to be like if you go around the side. It's going to be constant because, once again, the symmetry demands that only, okay, if it's infinitely long, elevation can't matter. And if cylindrically symmetric, the angle around it can't matter. So all that can matter is the distance away. So if we're the same distance away from the wire at all places, it's got to be the same electric field. So this is going to be the electric field multiplied, well, E is constant and E is parallel to dA. So dot, 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 because we've seen all of the rest of the steps. The flux on the side is equal to EA. What's the area for the side of a cylinder? There's a real easy way to get that answer.
Height times circumference, right?
It's circumference times height. And if you don't see that instantly, just think about taking the cylinder, slicing it, and flattening it. You'll have a rectangle that's bottom is the circumference and height is the height. And so area of a rectangle is base times height. So that's equal to the electric field times circumference is 2 pi r multiplied by the height. Finally, the electric flux on the bottom. What's the electric flux on the bottom of my cylinder going to be? 0, like top. I'm just going to, no reason to repeat what I said on the top because it's the same situation. So now I've done the left side calculating the fluxes. I've done the right side calculating the charge enclosed. I set the two equal to each other and I can find the electric field. So apply Gauss's law. Which I just rewrote there. So doing the application, that gives me E2 pi RH equals the charge enclosed, which was lambda H, divided by epsilon 0. Now notice there's a variable here that we don't have a number for, H. Right? H was the height of my Gaussian box, or Gaussian cylinder, I guess. We call it Gaussian pillbox. That's what I said, box. H was the height of that little Gaussian pillbox. But it doesn't matter because it's going to cancel out. It had better not matter. If it matters, we made a mistake. Right? If it matters how we arranged our surface to what the actual electric field is, well, that can't be true. The electric field has to be independent of how you calculated it. And so just dividing by 2 pi RH, you end up with where, once again, I just used the definition that K is 1 over 4 pi epsilon 0. So 1 over 2 pi epsilon 0 is 2K.
Could you repeat the K part one more time?
Yeah, the definition of K is that K is equal to 1 over 4 pi epsilon 0. K is just a constant of convenience to make it easier for us to do a lot of calculations. It's based on the fundamental constant permittivity free space epsilon 0. And so you just multiply top and bottom by 2, and you see that 1 over 2 pi epsilon 0 is 2K. Or multiply everything by, yeah. Didn't say that very well, but yes. How is this interesting to you? To me, it's interesting. How is it interesting? What was the relationship with radius for the electric field moving away from a sphere? 1 over r squared. From a wire, it's 1 over r. Right? So it changes that relationship. It doesn't drop off as rapidly. Why? Because we're having contribution from higher and lower pieces of the wire. As you move farther away, farther down becomes more significant. Right? If you're really close to the wire, most of the electric field due to something down here is vertical. There's just a very small horizontal component. But if I move out here, now most of the component from that same place is horizontal. And so that's what allows it to have the 1 over r instead of 1 over r squared. The amount of charge that's actually contributing to the electric field gets bigger as you move farther away at a rate proportional to the radius. So that's the electric field. Now, once we know the electric field, we could, of course, calculate the voltage. Because how does voltage relate to electric field? I'm going to put E dot dr. And so the electric field is going to be parallel to dr. And so it's just going to become E dr for my calculation. And so voltage going from distance away RA, distance away RB. What do you get from that? And I showed putting the limits in right off the bat, right? You would have natural log of RB minus natural log of RA. Well, natural log of RB is uncalculable because you have units. But if you use the rules for natural logs, that natural log of RA or RB minus natural log of RA is natural log of RB over RA, then the units cancel and you can actually calculate. I'm sorry, you can't see. So we can calculate the voltage as we move away from the wire as well. That involves calculus. So there's a little bit of calculus, right? Any questions about the wire? Because you have some wire problems on your homework, right? Yeah.
Just a general question for the whole assignment. So, I mean, like here we just kind of stated the sewed and the dot because we didn't want to go through the integration. In our homework, though, should we go through that every time? That basic
Well,
law integration to show.
You should, for each problem, you should do it once,
Okay.
right? You don't need to do it like, I said, like the top for bottom. Don't need to repeat it within the problem. But yeah, I want to see that you understand the reason you got from A to C each time. Okay. Which statement is true about the electric field inside of a conductor? Okay, I heard a B. Everybody's down with that? Good, because that's the correct one. That's also very useful to us. In fact, we utilize it. Nice, huh? I just changed it to white font so it would show up, but of course what's on the background shows up. So here we have a situation of two concentric spherical shells. I think I did this in class. If I make my Gaussian surface like this, what's the charge enclosed? 0. And thus, what's the electric field? 0. How do we know? Well, we had lots of good arguments. If I make my Gaussian surface like this, then which charge is enclosed? All of the charge that was on the inner one. And so this problem gave that the solid conducting sphere has -16 and then the outer one is +8. So this had, come on. So the charge enclosed is -16 microcoulombs. I'm not going to go through the rest of it because we know that outside of a uniform sphere, the electric field is the same as if the charge was at the center. So I'm not going to worry about using Gauss's law here. We could have figured it out without using it at all. What if I move my Gaussian surface out to here? Okay, that's perfectly in the center. What's the electric field at all points on that Gaussian surface? 0 because it's once again inside a conductor. If it's 0 for the electric field everywhere, then what's the flux through the surface? 0. Hence, how much charge is enclosed? 0. So there's minus 16 microcoulombs at the center. So how much charge has to be on the inner portion of that surface? Plus 16. So we use Gauss's law here. Once again, we didn't actually do any real calculation except for addition, subtraction, to get that there is plus 16 microcoulombs on the inner surface. Now this entire hollow shell has plus 8. So if I have plus 16 on the inside, how much do I have on the outside? Right. So it's got to be minus 8 on the outside. And then I can calculate the electric field going out because the total charge enclosed is minus 8. It's spherically symmetric. So it's going to behave as if it was a single point charge of minus 8 microcoulombs on the center. So I used Gauss's law here to calculate the charges on the surface. And it was so trivial I didn't write any equations down. We just did it in our head because we can add and subtract with the best of them. Everyone in here can add and subtract with the best of them, am I right? Probably multiply and divide too. So yeah, there's electric field lines. Now, there are two things I need to cover. One of them is really trivial. So trivial that I didn't look it up before class. Gauss's law has both an integral form and a differential form. And the differential form is that del dot E is equal to, oh, come on. There's something on my screen I'm trying to get rid of it like a smart person. Del dot E is equal to the charge density function, I think. There's also a constant here. I have to look it up. But you have one problem that gives you the electric field as a function of height and then asks you to find what the charge density is as a function of height. So what do you do there? Well, what is this del operator? It's a directional derivative. And so it goes like this. X hat partial with respect to X plus Y hat partial with respect to Y plus Z hat partial with respect to Z. Now there is a constant here. I think it's over epsilon 0, but I could be wrong. So I'll send you an email with what the actual form is after class. I didn't look it up. So if you have, it gives you the electric field vector is E0 times some function of Z in the Z direction. So if my electric field is some function of Z in the Z direction, when I do a dot product between that function, that electric field in the Z direction and the directional derivative, what do I get? Dot product is multiplying which parts? Parallel. So if my electric field is exclusively in the Z direction, then what do I get when I do the dot product? Yeah, just the partial derivative with respect to Z. You can calculate partial derivative with respect to Z, can't you? And then you just have the constant epsilon 0 to take care of. And so it actually turns out to be super simple. You just take a single derivative, multiply by the constant, and you have your answer. Yeah.
But how do we plot it? Because it says the first part of that is to plot the electric field as a function of elevation.
Well, you plot it, just say, I'm plotting the electric field in the Z direction. Since this is all in the Z direction, you just plot that function. So, what is the function?
E is equal to negative E sub 0, A E to the negative AZ, plus B E to the negative BZ times Z hat. And that's an alpha and a beta, not a beta.
Oh.
Sorry.
Okay, so we have that. So when you plot that, you have two exponential decay functions, right? And if you're given numbers, you can actually plot it. If you're not given numbers, you just have to kind of assume numbers. It gives you numbers, I thought.
It gives E sub 0 is 250 newtons per coulomb.
But it doesn't give you anything that's A or
It
alpha,
says that
B
they're
or...
all positive constants.
Okay. So in that case, what I would do is just say, what does an exponential decay look like? Right? You have two exponential decays, but since you don't know the constants, let's just say, what does an exponential decay look like? And so then I would plot that.
So the two added together would still just look like an exponential decay.
For the most part. There would be a subtle difference, but it depends on what the values of A and B are. And since we don't know them, we know they're both positive, it's going to look pretty similar to an exponential decay. Question?
So we could just kind of stick in a 1 for each of those and graph with that general shape.
Yeah. Okay, now the last thing. The last thing is the problem that has an infinite plane or an infinite sheet with charge of a given charge density. So it has to be an insulator if you have a charge density, right? If it was a conductor, it'd be just on the surfaces. So what you're going to have to do there is decide what kind of exploitable symmetry does this have. It has an exploitable symmetry. Which of those three that we've asked would it be? Spherical, cylindrical, or planar? It's a planar symmetry. And so then you need to come up with a shape that fits this geometry. What direction is the electric field? The charge density, I think, is positive, right? So what direction will the electric field be pointing from this surface? It's going to be vertical. So what shape is going to be either parallel or perpendicular to that direction on all sides? I think I heard the answer.
More sheets.
No, not more sheets. It needs to be a closed surface that we can use for calculating with Gauss's law. Let's start with the clearly wrong answer. Would a sphere match this symmetry? No, because we have changing angles everywhere. So what are we going to need to match the symmetry? Okay, we need flat top and flat bottom, and we need the sides to be vertical, because vertical would be, no flux. And so you could use a cube, you could use a, square, well, what do they call it? A right parallelepiped. I think it's right rectangular parallelepiped, actually. Or a cylinder. I always choose a cylinder because that minimizes the surfaces, only 3. Where do you place the cylinder? You have 2 choices. It works either way. You can either make it so the center of the cylinder is at the center because of symmetry, right? Because of symmetry, the electric field's going to have to be 0 at the center. Or you can make it so it's symmetric, so you go up and down by the same amount from the center. Either one of those works. And you'll have to calculate the charge enclosed. Obviously, the charge enclosed is smaller and proportional to Z if you're smaller than the thickness, and then it's constant if you're bigger than the thickness. And you go through your calculations, and you'll find a maybe not stunning result when you're all done. When you're all done, you'll have it's a function of Z, the distance away. And what do we find if it was a point charge? A function of 1 over r squared, right? If it was a line of charge, then it became what? 1 over r. So what do you think it would be if it's a sheet of charge? So we've gone from 0-dimensional to 1-dimensional, now to 2-dimensional charge distribution. Not 1 over square root. We went from 1 over r squared to 1 over r to the first. Okay, go ahead and do the calculation. It will make sense when you get there. It's not natural log. But to me, it's really shocking at first. And then I have to think about just what I thought about with the wire. As I get farther away, it's in 2 dimensions now that I'm having more charge contributing. And if you have any questions, come talk to me or send me an email. It's better come talk to me because I can explain things better. And I don't just give you the answer. Giving you the answer doesn't help you very much when it comes to test time. Okay,